Hello friends, welcome to Follow Up. In this video, we're going to continue our series on Kahn's algorithm. So here we're going to look at problem 2.10, cost schedule 2. So before we start, let me give you a quick overview of this video. So in this video, we're going to use Kahn's algorithm to address this problem. So Kahn's algorithm basically is a multi-source breadth-first search or breadth-first traversal algorithm within degree for topological sorting. So let's briefly look at the problem statement, and then we do the coding. And in between, we're going to explain some crucial points. So here we are given a number of causes. It's called num causes. I'm going to call this number n, right? So the causes are labeled from 0 to this n minus 1. And we are also given an array called prerequisites, which actually describe the first and last relations between the causes, right? So for example, this AI, BI means that in order to take cost AI, we need to first at least finish cost BI. So overall, if we want to take a course, we need to finish all its prerequisites. So that's the meaning of this sentence. So here we want to return the ordering of courses we should take to finish all courses. And if there are many valid answers, we're going to return any of them. So if it's impossible to finish all courses, we're going to return an empty array. So here we have 3 examples. In example 3, so there are 1 courses. Therefore, they have no prerequisites, so we just need to finish this course itself. Well, in the first example, we have 2 courses. Course 0 is the prerequisite for course 1. Also, it's the only prerequisite, so we first finish 0 and then finish 1. So this is the A topological ordering. So when I say A, which basically indicating that topological ordering in general is not unique. So you will see why this is true if we look at the algorithm. So in example 2, so the output is 0, 2, 1, 3 if you examine the graph, right? So with that said, let's also quickly look at the constraints. So here the number of courses is bounded above by 200, and the prerequisite length is bounded by this number, right? So this number, if we make it equal, it means that any 2 courses, there will be a directed path or edge. So and all the pairs are distinct. So with that said, we are ready to look at the coding. So here, one task I want to mention is that when we finish the reading, the coding, we also explain why the topological ordering in general is not unique. So here, step 1, I'm going to make some preparations. For example, get the in degree and build this graph and initialize, right? So here I'm going to use this in degree. So we have I0 for I in a range M. So notice that here the indexing order is from the 0 indexing, in other words from 0 to n minus 1, both inclusive. Then the graph, I'm also going to use this format. I'm going to use list dictionary comprehension, right, for I in range M. So the set for each of the node will be used to store the neighbors, right? And then let's do some initialization. So because here we know that this relation means BI is a prerequisite of AI. So we are going to write this for end start in this prerequisite. So we're going to get this graph start. So we're going to add end, indicating that end is one neighbor of the start. And also this means that there is a direct edge starting from start and pointing to end. In such regard, so we want to increment the in degree of n by 1. So once this done, basically we finished the first step. So now let's make some further preparation. So get the initial queue for multi-source breadth-first-based search. So here we want to find those courses which have no prerequisites. So in the graph language, it means that we want to find the courses that has in degree 0. So here I can use a list comprehension, course for course and degree in degree items if d equals 0, right? So actually, this queue as a verb in each step, it might be not just a one element or single element. And when we do the breadth-first search, so we can look at any of the courses first. So this is also why, in general, for the topological ordering, it's not unique, right? In general, not unique. So now let's do the traversal. So we can see to continue, right? So the traversal part. So this is a very standard well queue. So but we want to take into consideration of this problem requirement. We want to return one of the topological sorting order. So for this, I'm going to see, let's initialize a result variable. So once we finish a course, we are going to append to the result. So this result will hold the topologically sorted courses. So well queue, so let's get the course. So it's queue pop left. So in other words, here I use the deck container, I just use it as a queue. So we can first in, first out, right? So once we do this, so we are going to append this course to result, and then we are going to examine its neighbors. So for neighbor in graph course, right? So because we have finished the current course, so we know previously there's an directed edge from course to this neighbor, right? Therefore, the in degree of this neighbor is decremented by 1. So once we finished the update for the in degree, we want to check for the current neighbor if all the required prerequisites of this course neighbor are finished. If so, we're going to include that, so to proceed or finish later. So we want to check if in degree of neighbor is 0. If so, we want to include that, right? So append neighbor. So once we done this while loop, so basically we should expect to get a topologically sorted list. However, it's possible that we cannot finish all the courses. So therefore, when we do the return, we want to return result if the length of this result equals n. Otherwise, so we're going to return an empty list. So this is according to the problem requirement. So up to now, I guess we finished a format of coding. So before we make any further comment, let's first make a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So now I guess we are ready to make some further comments. So here actually we can make a running variable courses initially 0. So once we do the append operation, we can count it, increment by 1, and then later we just need to check if n courses equals n, right? So now let's test it. Yeah, it passes all the cases. So this is the one point we want to notice. The second point we want to notice is that here we are dealing with directed graph. Therefore, when we do the while loop for traversal, we didn't use set data structure to aid the traversal or to avoid repetition. So this is the second point. The third point I want to mention is that for topological ordering in general, it's not unique. So it's due to the way of doing traversal, because here we are doing multi-source breadth-first search. Each tab in the queue, as long as the courses are in the queue, so they can be proceeded in any order. So this is also the source of non-uniqueness, right? So with that said, I guess that's about it for this current video. Thank you.